Thank you. Hello, everyone. So, I'll tell you something about distributed representation of text and its applications. So, first, why bother with distributed representation? The fact is that when we have audio, for example, we have dense representation of data because every value has non-zero, is non-zero, similar images. For every pixel we have some value that has that carries some information value. And there's problem with text when we have like df by df. For example, let's take a document. Not every word occurs in every document, so the representation is rather sparse. And that's why we should use distributed representation of text to model its features more efficiently. So what is it? Basically, words are mapped to vectors. So imagine that we have multi-dimensional space, and every word is mapped to a vector in this space. Next, why is it called distributed? Because I assume that most of you imagine some distribution across machines when we talk about distributed. So it's different here. Distributed means that word features are distributed into multiple values of the vector. And it's based on distributional hypothesis that words are similar if they appear in similar context. So context means that if we have a sequence of words, a word in the middle of those of the sequence appears in context of those words. So if there are multiple words that can occur in similar context, we know that those words should be similar in some aspect. Okay, and the fact that we have multiple values in a vector, in every vector of word, means that we have multiple degrees of similarity because we can compare multiple values, not just two numbers, but vectors. Most of the time it's done by cosine similarity. So that means we can do also vector representation, vector operations like addition, subtraction, and so on. For example, if we sum up vectors for words like car and wheel, we get a combined meaning of those two words. And we can also represent some relations as vectors. Let's take biggest minus big plus small. It's very close to smallest. It's not exactly the vector for smallest, but it's very, very close. So it's similar with semantics. When we take Paris minus vector for France and add vector for Germany, we get something very close to Berlin. So it's rather cool to work with words like with vectors. Here are some other examples of relationships that I took from original paper about efficient estimation word representations. So, for example, we can represent relation for capital city, currency in a state, city and state, man-woman relationships like brother, sister, grandson, granddaughter, adjective to adverb. So these are basically some semantic relationships, and these are syntactic relationships. So the vector representation can capture both semantic and syntactic features of words. So next, word2vec is a keyword that you should remember when you want to work with this representation. It's an open source tool from Google researchers. It was open sourced in 2013, and it can learn word embeddings, which are basically some mapping of words into vectors. That's another why I call it now word embeddings, is that I want you to know that there are multiple names for the same thing. So word embeddings are basically the same as distributed representation of words or continuous feature vectors of words. So if you come across this, you will know. And word2vec is efficient parallel implementation in C of learning word embeddings. So that's basically why is it so popular. You can visit this homepage of word2vec, and it has multiple tasks implemented. So I will talk about it later. Probably more interesting for you is that word2vec is also in Gensim package. It's in Python, so it's easily to get hands on in Python. So we import just package. We have some sentences which where every sentence is basically array of or sequence of words. And we just create some object based on this. Actually, this min count parameter is just for correctness of this code, because what does it do is that we learn the representation of every word that occurs at least once. By default it's 5, because there are many words which it doesn't make sense to learn embeddings of words that occur just once in the whole data set, so that's why it's here. And next we have some multiple parameters that we can tweak. For example, size of the vectors. So basically, what's the capacity of our model? What number of features can we represent? And workers means how many parallel threads do the learning. Okay, so apart from that, we can just create object without training at the same time, because we can have different sets for building vocabulary and for training. So I should mention also that when we create this object, we pass through sentences 2 times, because we need to build vocabulary and then we need to do the second pass to train the model. So this is just another way of doing it. And then we can save, load the model. We can load the model in origin word2vec format, which is based on the C implementation. Apparently this is faster, because it takes advantage of Python native binary format. Okay, and what you can do with distributed representation, I chose three basic practical things that you can do. First is word analogy. You can ask okay, I have prepared. I'm not sure if internet is working. Right. So I can show you online demo of this. So word analogy works like this. We give it. give man is to king as woman is to what. So we can put there some words and it answers queen. Okay. So next thing what we can do is get the most similar words for some query words. It is better. So let's take iPhone. So we can get most similar. We chose iPad. In fact, there are multiple answers here, ranked by the similarity score. So there's iPad, iPhone with big I in the beginning, and so on. So you can handle multiple capitalizations of word with this tool as well, with this representation. And last but not least, you can take multiple words and discover which one does not fit into this sequence. So dinner, cereal, breakfast, lunch, apparently cereal. Okay, so it's start playing. So how do we do it in code? So we can retrieve most similar words in multiple ways. We can put as parameters positive and negative words. So now we know that it's basically the word analogy. If we take king minus man plus woman, it should be queen, and we can see the similarity score as well here. If we use doesn't match, it basically reveals that cereal doesn't match here. We can measure similarity between two words, woman, man. We get some score, and we can just get a raw numpy vector of a word like this. Now, what's the great thing about this is that we doesn't need to bother with things like ontologies and various relations among words. Like when we work with words, we need just most similar words to broaden our understanding of some word. And other way would be that we take some synonyms, antonyms, and I don't know what other hacks we could use. This is very easy compared to that. Okay, and another cool thing you can do with that, you can visualize those vectors in 2D with a tool called tsne. It has multiple implementations in multiple languages, so that's very practical as well. You can see here basically it's basically a tool for dimension reduction. So every word has, let's say, 300 features because it's a vector, and we can reduce this to two numbers, two coordinates in a plane like this. So we can see that similar words are close to each other, and that's useful in multiple use cases. Okay, so how do we do it in the code? So some imports. This needs, for example, in scalar and manifold package. It's basically scikit. Well, scipy. Yeah. So let's take x as some array of vectors. So now we have 4 vectors. Each has 3 dimensions. We create some object tsne where we tell it that it should have 2 components because we want it to display in the plane, in 2D plane. So we fit it, and we get resulting to the coordinates of every vector. Okay, so some closing contemplation of how could you use this distributed representation in your e-commerce business, or I don't know what you are working on. I tried to come up with some interesting use cases which are similar to words and text. So you could use Word2Vec, for example, on web pages visited by users. If we map web pages to words and users to sentences, basically when user in a session visits multiple web pages, you can learn what web pages occur in the similar context and learn embeddings of web pages. So that's first useful use case. Or if we have some documents bookmarked by users, you can again consider documents as words and users bookmarking documents as some sentences. So if document occurs, multiple documents occurs in the bookmark sequence of user, they should be similar. And then we can take products viewed or bought by customers. So if multiple products are bought by the same customer or viewed by the same customer in a session, we could also assume that they should have something similar. Okay, so these are just starting thoughts for you to think about how you could use this in your particular domain or business. And at last, I have some resources. So at WordNet homepage, you can download pre-trained models of word embeddings for English language, which were trained on 100 billion words of Google News archive. At Gensim, you can find here a tutorial how to work with Word2Vec, so there are more details. And also, if you are interested in learning word representation, you can dive into more research-oriented and more neural network stuff in terms of the tutorial. So thank you for your attention. If you have any questions, I will